For decades, we've been on this massive hunt for dark matter, right? Searching for some kind of mysterious particle. But what if we've been looking in completely the wrong place? What if the secret isn't a particle at all, but it's hidden in the very geometry of reality itself? You know, the search has always been for a particle. Maybe a WIMP, a weakly interacting massive particle, or something even more exotic. But this radical new idea starts by asking a really provocative question. What if we've had it all wrong? What if dark matter isn't even a thing in the first place? What if it's something way more fundamental? This theory is proposing that dark matter is, well, it's basically a shadow. It's not made of matter like you and me. Instead, it's a gravitational echo, an effect cast by the deep, hidden geometric structure of space-time. And here's the part that is making physicists' heads turn. This theory claims it can predict the structure of dark matter in galaxies from the ground up, with absolutely zero adjustable parameters. Now, in physics, that is the holy grail. It means the theory isn't just being tweaked to fit the data. It makes a hard, concrete prediction that's either right or wrong.
Okay, so to really get why this is such a bombshell, we need to talk about the huge problem it's trying to solve. It's one of the most famous puzzles in cosmology, a big disagreement between our theories and what we see, and it's called the core cusp problem. So here's the deal. For years, our very best computer simulations of the universe, based on our standard model, which we call lambda CDM, had been predicting one thing about how dark matter should clump together. But when astronomers actually point their telescopes at real galaxies, they see something totally different. And that's a major crack in our understanding of the cosmos. And the problem boils down to this. On the left, you've got the prediction. The simulations say dark matter density should skyrocket toward the center of a galaxy, forming this really sharp, pointy cusp. But on the right, well, that's reality. When we look, we see that the density flattens out into a plateau, a core. And that cosmic mismatch is exactly what this new theory claims to fix. So, how does this new approach solve it? It basically throws the whole particle idea out the window and starts looking for the answer in the mathematical blueprint of the universe itself. It suggests that space-time has this hidden geometric sector, and that's where dark matter actually lives. The whole theory is built on this really cool mathematical object called the Grassmannian, GR24. Now, okay, that sounds incredibly complicated, but think of it like this. If space-time is a giant city, the Grassmannian is the ultimate master map of every single possible straight road through that entire city. It's the geometric blueprint for every path a ray of light could ever take. So according to this idea, that master blueprint isn't just one thing. It actually has two totally separate perpendicular parts. There's the visible sector, which is, us, our universe, everything we can see and touch. But then there's this hidden shadow sector, and that shadow cast by the geometry itself is what we experience as dark matter. So, how do we get from some abstract math to a real prediction? It's actually a pretty elegant two-step process. First, the theory says this hidden geometry casts a two-dimensional shadow onto the boundary of our universe, what we see as the night sky. And then, a totally locked-down mathematical rule called the Abel inversion lets physicists perfectly reconstruct the 3D dark matter cloud from that 2D shadow. It's a direct one-to-one translation. And that brings us to the prediction. This isn't just some vague philosophical story. This geometric framework leads directly to a precise, hard number that we can go out and actually test against reality. Okay, here it is. This is the formula the theory predicts for dark matter density. Now, you don't need to be a mathematician to see the key part here. Look what happens as you get close to the galaxy's center, when the radius, r, gets close to 0. In those old cusp models, the density would shoot off to infinity. But here, the math naturally works out so that when r is 0, the density just becomes a simple, finite number. It has to have a flat core. It's built right in.
And I really want to hit this point home because it is so important. This is not a model that was designed and tweaked to match what we see. It's presented as a mathematical theorem.
The shape of this dark matter profile is a direct consequence of the geometry. There are no knobs you can turn to make it fit better. It is what it is.
And the theory goes even one step further. It doesn't just predict the shape of the dark matter core, it predicts its size. For our very own galaxy, the Milky Way, it calculates from pure math that the dark matter core radius should be 9.98 kiloparsecs. And just for scale, a single kiloparsec is more than 3,000 light years across. So how does that prediction stack up against what we actually measure? This is just stunning. The geometric prediction is 9.98 kiloparsecs. Our best astronomical observations from looking at how stars and gas move tell us the core is somewhere between 6.5 and 10.5 kiloparsecs. The prediction lands smack dab in the middle of the observed range. To get this close with zero free parameters, I mean, that's either the luckiest coincidence in history or something truly profound is happening. But here's the thing. Great science isn't just about getting things right. It's about being testable. It has to stick its neck out and offer clear ways it could be proven wrong. And this theory does exactly that. This whole framework makes 5 sharp, falsifiable predictions. It says all galaxies must have these flat cores. It says dark matter shouldn't interact with itself. And this is a big one. The core sizes should be pretty much universal, all around 10 kiloparsecs, no matter how big the galaxy is. It also predicts subtle differences in gravitational lensing and in the patterns of the very early universe. Every single one of these is a hurdle the theory has to clear to survive. The author, Daniel Tupin, sums it up just perfectly. Dark matter is not a particle species. It is the shadow sector of the celestial conformal field theory. That last bit, celestial conformal field theory, that's the technical name for this entire geometric way of thinking, this whole new way of looking at the universe's blueprint. And so that leaves us with this really incredible thought. We've spent half a century, billions of dollars, searching for a new fundamental particle to solve this giant puzzle. So what if the solution wasn't a new piece on the board at all, but the discovery that the board itself has a completely different shape than we ever could have imagined?